Welcome back to Derivability. Today we're going to take a look at the velocity and acceleration of a particle using rotating axes. Okay. Now, maybe you've already seen my video on planar kinematics of a rigid body. That's going to be very helpful for you to watch before this one. This is going to make a lot more sense. It's kind of based on that one, but that's just a natural prerequisite. Okay, so if you want to, pause the video right now, go back to the channel, and watch that other one, planar kinematics of a rigid body. Okay, all right, so if you've seen that previous video, the setup here looks very familiar, probably. We've got a fixed origin O, with some x and y axes. The blue outline here represents some generic shaped rigid body rotating in the xy plane. Okay, A and B are a couple of points on this rigid body. Okay, and we have a double subscript scheme for labeling positions, velocities, and accelerations. Okay, so I've got those position vectors labeled on the axes on the diagram right now, and the equation written in the black marker to your right. Okay, so position R sub BO equals R sub BA plus R sub AO. Okay, now the new thing here, the new twist, in addition to this rigid body rotating, what we're going to imagine is that at the moment in question, we've got some object that happens to be at point B. I'll just draw this little green dot here. And maybe this object is following some path. Okay, maybe it's literally on the rigid body, or just maybe with reference to some rigid body. Okay, this would be like some object on the Earth that happens to have a certain motion measured from or relative to the Earth, but we understanding that the Earth is moving through space and rotating. Okay, so for instance, what we're going to try to write down is the velocity and acceleration of such a particle as viewed from outside the rotating Earth. Okay, so let me just make that a little bit easier to see there. Okay, all right, so let's proceed the way we did in the other video. Now it's going to be a little different. Okay, what we need to do to go from position to velocity is to take time derivatives. Okay, so what we're getting now is on the left side velocity BO. Okay, but here is where we run into some new things. Okay, first, point B on this rotating object, it's a fixed distance from A. Okay, now I'm not talking about the particle that happens to be at location B, point B, but the point itself. It's a fixed distance from A. So the only way in which it can move with respect to A is via some rotation. Okay, and we figured out in the previous video that's going to take the form of this cross product omega cross R sub BA. Okay, now I'm going to leave a little blank space here and go to the end. And then the time derivative of R sub AO, well, A has some sort of motion with respect to O. So that time derivative is velocity AO. Okay, but the new thing here is the fact that this particle is moving with respect to the rigid body. Okay, it's as if we have got some little coordinate system. It can pass through A, but it doesn't have to. Okay, say X. Sometimes we call these X prime and Y prime axes, which are themselves rotating along with the rigid body at the rates omega and alpha. Okay. But this particle, which just happens to be at point B right now, itself is moving with respect to the rigid body, or at least with respect to these rotating coordinates. Okay, so there are many ways of notating this. Okay, I'm going to write it this way. Velocity subscript BA, but with respect to that rotating body, or the rotating frame of reference. Okay, so there are a few distinctions here. Okay. All right, velocity AO, I think that's evident, especially if you've seen the last video. That's just the motion of A with respect to O. Okay, now omega cross R sub BA, this has to do with the motion of point B. Okay, so point B is like a landmark on this rigid body. Okay, now velocity BA in this rotating frame, this has to do with the motion of a particle that just happens to be at B at this moment. And then velocity BO kind of incorporates both of those. Okay, and what it does is it has to do with the motion of the particle. Okay, but as viewed from outside this rotating frame of reference. Okay. All right, so what I have written in blue marker right here, this is the new thing compared to the formula we had in the previous video. Okay, everything in this equation that's written in the black marker, well, that we discussed that before. Okay, but now we have this new thing. Okay, now we're also interested in a formula for the acceleration of this particle that happens to be at point B relative to an outside origin O. Okay, and we'll take a look at that next. All right, well, now let's take a look at acceleration of B with respect to O. And again, this is going to be the acceleration of some particle that happens to be at point B at the moment we are interested in, the moment that we're showing in our diagram. Well, naturally, to get acceleration, we want to take the derivative of this velocity formula, okay, with respect to time. All right, so left side velocity BO, okay, its time derivative is going to be acceleration BO. That's what we're trying to find the formula for. Okay, now this is going to be a little more complicated. All right, so first, I've got this first term, omega cross R sub BA. Right. Well, that's a product. So in some sense, we're going to have to use a product rule and, some other things here as well. So the time derivative of omega is alpha. Okay, so we're going to have alpha cross RBA. Okay, but then we have to account for the fact that the body is rotating. Okay, so the change in this velocity, you might say here, that's represented by omega cross BA, well, there could be a change in its rate, but also a change in its direction. So we're going to have omega cross RBA. Okay. All right. Now, once again, I'm going to leave a little space here and write a term in the blue marker here in a moment. Okay, but I'm going to go on to the next thing, and the next thing is leaving a little space. Okay, and also the next thing is leaving a little space, and then finally I'm going to go to the very end. And I'm going to take the time derivative of velocity AO, and I'm going to get acceleration AO. Okay? All right, so the stuff that I've written in the black marker, that's exactly what we saw in the last video, when we simply had the rigid body, and we were concerned about the motion of point B on the rigid body. Okay? But the three other terms that I'm going to write in blue actually have to do with the motion of the particle, which happens to be at B. So let's go back to the omega cross RBA, and we did a product rule to obtain these terms, but also when we take the derivative of this R sub BA, we also are keeping track of, well, the motion of the particle at B, not just the point B. So what we're going to get there is the omega, which is already there, cross, and then we're going to get another term of the sort we talked about in the previous formula. The RBA, in terms of particle motion, turns into velocity BA in this rotating frame. In other words, it's the same as this thing. Okay. All right, now moving along to taking derivatives of this thing, velocity BA in the rotating frame. Well, it's in the rotating frame. So its derivative can be thought of as a cross product. Omega cross VBA in the rotating frame. Okay, but one more thing is then there's the actual motion of this thing in the rotating frame. This object at B, this particle at B, could be accelerating. So I'm going to call that acceleration BA in the rotating frame. Okay, now we're not quite done with this, because you might notice that I've got two terms here which are identical. Okay, so I just double that. Okay, we're going to algebraically combine those, simplify. All right, so what we're going to have here finally is acceleration BO equals alpha cross RBA plus omega cross, the grouping omega cross RBA. All right, then plus 2 omega cross velocity BA in the rotating frame plus acceleration BA in the rotating frame, and then finally plus acceleration of A with respect to O. Okay. Now, as I pointed out before we transitioned here to talking about acceleration, some of these terms, are due to the motion of point B, and some of them are due to the motion of the particle that happens to reside at point B at this moment. Okay, well, first, acceleration of A with respect to O. Well, A just has kind of whatever motion it has with respect to O. Okay, basically the terms I have written in black, okay, these refer to the motion of point B. In other words, it's some landmark on this rigid object here, if you like. Okay, the ones that I've written in blue, the new ones, those have to do with the motion of the particle we are talking about that just happens to be at point B at this moment in time. And then acceleration BO, this actually takes both of them into account. Okay, so really it's talking about the motion of the particle, okay, but just from outside this rotating frame of reference. Okay, a couple of final thoughts here. All right. If you happen to have planar rotations, which is essentially what we're talking about right now, okay, this term that I'm underlining here can actually be resolved to something a little bit simpler, negative omega squared R sub BA. Okay, and this comes from what we call the back cab rule. in vector analysis. Okay, also, the term that I'm putting this wavy overline on, that is sometimes referred to as the Coriolis effect. Okay, and that has to do with objects moving in rotating frames. Okay, especially over long distances, relatively long distances, or relatively long times. So, for instance, the Earth is a rotating frame, and there are masses of air, weather patterns, moving over large distances over long periods of time on a rotating Earth. Maybe projectiles or aircraft, like missiles or what have you. Aircraft. This Coriolis effect is pretty important in terms of navigation. Okay. All right, well, I hope that this has been helpful. Thanks for hanging around here. Thanks for stopping by. I appreciate that. Might consider giving me a like or subscribe. Share this video with other people you know who are studying this. Okay, and hope you'll drop by for the next video.